Every star in the sky is dying right now. You just can't see it happen. A star's death takes anywhere from a flicker in cosmic time to 100,000 years, and no two deaths look the same. Some stars fade like a dying ember. Some detonate with enough force to outshine an entire galaxy. Some collapse so violently they tear a hole in spacetime itself. There are at least 8 distinct ways a star can die, and which one you get depends on one number: mass, not personality, not composition, not luck. Mass, decided at birth, locks in an ending the star can never renegotiate. A star 10% more massive than the cutoff gets an entirely different death than one 10% lighter. There's no appeal process. Every single star that has ever existed, roughly 100 billion of them in our galaxy alone, is already walking one of these 8 paths, whether it's 1 million years old or 10 billion. Let's go through every single one. In order, starting with the quiet one, the red giant. This is where it all begins going wrong. Every star, including our sun, spends most of its life in a stable tug of war, gravity pulling in, fusion pushing out, hydrogen fusing into helium in the core, a balance that can hold for billions of years. But here's the thing: fuel runs out. Once the hydrogen in the core is gone, the core contracts and heats up, and the outer layers respond by doing something strange. They expand massively. Our sun will swell to over 200 times its current size, swallowing Mercury, then Venus, and reaching close enough to scorch Earth to a lifeless cinder if it doesn't engulf it outright. Surface temperature drops. The star cools to a dull, bloated red. That's the giant part. For stars like our sun, this phase lasts around a billion years. A billion years of slow, glowing decline. Here's the fact that changes everything. The core, meanwhile, is doing the opposite. It's shrinking, heating, starting to fuse helium into carbon and oxygen, buying a little more time. The asymptotic giant branch phase pushes the star into wild pulsations, its outer layers heaving in and out over months at a time, shedding material into space with every breath. This is a star actively coming apart, one exhale at a time. Somewhere out there, a star exactly like ours is doing this right now, breathing its last breaths across 10,000 years, utterly indifferent to whether anyone is watching. Let that sink in. You can see this happening already tonight if you know where to look. Betelgeuse, the red shoulder of Orion, is a red giant in this exact phase, so large that if it replaced our sun, its surface would extend past the orbit of Jupiter. Aldebaran, the angry red eye of Taurus, is doing the same thing, slower. This isn't a rare event. It's the single most common next chapter for a star like ours, waiting quietly in a constellation you've probably looked at this week. Eventually, the outer layers have nowhere left to go. They start to leave for good. The Planetary Nebula, confusing name. No planets involved at all. Early astronomers just thought these round, glowing clouds looked like planets through primitive telescopes, and the name stuck for 300 years. What's actually happening is a star shedding its entire outer atmosphere into space, layer by layer, in a slow motion exhale that can last 20,000 years. The exposed core underneath, now blisteringly hot, floods the expelled gas with ultraviolet radiation, and the gas lights up. Reds from hydrogen, greens from oxygen, blues from helium. The result is some of the most photographed objects in the night sky: the Ring Nebula, the cat's eye, the helix nicknamed the Eye of God for a reason. But here's the twist: a planetary nebula is not permanent. It's a corpse's afterglow, and it fades. Within 50 to 100,000 years, the gas disperses into the interstellar medium, thinning out until it's indistinguishable from the background dark. The beautiful part is temporary. What's left behind is not. Every atom of carbon in your body, every bit of the oxygen you just breathed, was forged in a star and scattered exactly like this. You are looking at your own origin story, and it looks like a dying breath lit up in color. There's a second twist most people never hear. Planetary nebulae are often not simple spheres. They come in hourglasses, butterflies, spirals, and rings, shaped by hidden companion stars, magnetic fields, and spin, which means the same physical process produces almost no two nebulae that look alike. Everyone is a fingerprint of exactly how that particular star lived and who, if anyone, it lived beside. The gas goes, the core stays. And the core is about to become something almost unbelievably small. The white dwarf. Here's the fact that should genuinely bother you. This is the fate waiting for over 97% of all stars in the galaxy, including our sun. Once the outer layers are gone, what remains is the exposed stellar core, no longer fusing anything, just an ember of carbon and oxygen roughly the size of Earth. But cram into that Earth-sized sphere about 60% of the sun's entire mass. A teaspoon of white dwarf material would weigh about 5 tons on Earth. 5 tons. From a teaspoon, it holds itself up not through fusion, not through pressure in any normal sense, but through something called electron degeneracy pressure, a quantum mechanical refusal of electrons to occupy the same state. It's physics, not fire, keeping this thing from collapsing further. And a white dwarf has no more fuel to burn. It will simply cool, slowly, for an almost incomprehensible span of time. Current estimates put the cooling process at longer than the current age of the universe, meaning not a single white dwarf has ever fully gone cold. Not one. Every white dwarf that has ever formed since the universe began is still technically warm. Given enough trillions of years, they'll fade to black dwarfs, invisible, inert, drifting forever. The universe is currently about 13.8 billion years old. The theoretical time needed to cool a white dwarf to a true black dwarf is estimated in the quadrillions of years, roughly 100,000 times the current age of everything. That means black dwarfs are, right now, a purely theoretical object. Nobody has ever seen one. Nobody ever will, not for longer than almost any other number in this entire video. But there's one way a white dwarf story doesn't end quietly. One way it goes out with a bang loud enough to be seen from another galaxy. Type Ia supernova. This is the white dwarf's plot twist. A lone white dwarf, left alone, just cools down forever. But most stars don't live alone. Many white dwarfs orbit a companion star, and if that companion gets close enough, or if two white dwarfs spiral into each other, gravity starts stealing material across the gap. The white dwarf feeds and feeds. There's a hard ceiling on how much mass a white dwarf can hold before electron degeneracy pressure simply loses the fight. 1.4 times the mass of the sun, a number so precise astronomers named it after the man who calculated it, Subramanian Chandrasekhar. Cross that line and the entire star ignites in runaway carbon fusion all at once in about a second. Not a collapse, a thermonuclear detonation. The whole star obliterated, no remnant left behind. The detonation front races through the star at roughly 6,000 kilometers per second, fusing about half a solar mass of carbon and oxygen into iron group elements in under 2 seconds, releasing more energy than the sun will produce in its entire lifetime, and doing it in less time than it took you to read this sentence. Here's the twist that makes this one so important, because every type Ia supernova detonates at almost exactly the same mass. They all release almost exactly the same amount of light. That makes them standard candles, and astronomers use their known brightness to measure distances clear across the observable universe. This exact class of explosion is how we discovered the universe's expansion is accelerating, a discovery that won the 2011 Nobel Prize in Physics. A dead star's carefully calibrated detonation rewrote our understanding of everything, including the ultimate fate of the cosmos itself. And there's a strange irony buried in here. For roughly 2 or 3 weeks, the explosion of an object smaller than Earth can outshine every one of the 100 billion stars in its host galaxy combined. Astronomers on the far side of the universe tonight could be recording the death of a white dwarf in a galaxy they've never otherwise noticed, purely because that white dwarf just briefly became the brightest thing for 100,000 light years. But this is only how small and medium stars go. Stars far more massive don't fade, and they don't wait for a companion. They just run out of time. Core collapse supernova, also called a type 2. This is where mass changes the entire rulebook. Any star over about 8 solar masses skips the gentle white dwarf fate entirely. It keeps fusing heavier and heavier elements, hydrogen to helium, helium to carbon, carbon to neon, all the way up an accelerating ladder. Each stage burns hotter and faster than the last. Carbon fusion might last 600 years. Neon fusion, about a year. Oxygen fusion, 6 months. Silicon fusion, the final stage, lasts about one single day. One day of fusing silicon into iron, and then it stops, because iron is the dead end. Fusing iron doesn't release energy, it consumes it. The star has, in effect, run its engine into a wall it built for itself. With no outward pressure left, the iron core, roughly the mass of the sun, packed into a sphere the size of Earth, collapses in under a second. It falls in at a quarter of the speed of light. Here's the fact that changes everything. The core rebounds, slamming into infalling material, and combined with a flood of neutrinos, blasts the star's outer layers outward in one of the most energetic events in the universe. For about 10 seconds, the neutrino burst alone releases more energy than the entire visible universe emits in light. More energy than every star, every galaxy, everything combined for 10 seconds from one dying star. And almost none of that energy is light. 99% of it leaves as neutrinos, ghostly particles that pass through entire planets like they aren't there. In 987, a supernova in a nearby dwarf galaxy called the Large Magellanic Cloud, 168,000 light years away, sent a burst of neutrinos through Earth itself. Detectors on the other side of the planet caught them, meaning they passed straight through the entire mass of the Earth, first unbothered, arriving hours before the visible light from the same explosion. Because light gets slowed slightly fighting through the star's own outer layers, and neutrinos don't fight anything at all. The explosion can briefly outshine its entire host galaxy, visible to the naked eye in daylight for weeks, as happened with the supernova recorded by Chinese astronomers in the year 1054, whose remnant we now call the Crab Nebula. What's left behind depends entirely on how much mass remains in that collapsing core. Neutron star. If the leftover core is between about 1.4 and roughly 3 solar masses, it doesn't become a black hole. It becomes something almost as strange. Electron degeneracy pressure has already failed at this mass, so protons and electrons get crushed together into neutrons, and the whole core becomes an object made almost entirely of neutrons, held up by neutron degeneracy pressure. The result, an object with 1.5 times the sun's mass, packed into a sphere about 20 kilometers across, roughly the size of a city. A single sugar cube sized piece of neutron star material would weigh about 1 billion tons on Earth. 1 billion tons in a sugar cube. Because angular momentum has to be conserved as the core shrinks from a size larger than Earth down to 20 kilometers, the spin rate skyrockets. Some neutron stars, called pulsars, rotate over 700 times per second, sweeping beams of radiation across space like a cosmic lighthouse with a clock more precise than anything humans have built. The fastest known, PSR Joan 1748 minus 2446 AD, spins at 716 rotations per second. A point on its equator moves at roughly a quarter of the speed of light, meaning part of this dead star's own surface is nearly outrunning light itself. Here's the part that should genuinely unsettle you. The surface gravity is so extreme that if you dropped an object from 1 meter up, it would hit the surface at over 2,000 kilometers per second. Anything that fell onto a neutron star wouldn't shatter. It would flatten into a layer of atoms in a fraction of a second. Some neutron stars go even further. Magnetars carry magnetic fields a quadrillion times stronger than Earth's, strong enough that from 100,000 kilometers away, a magnetar could wipe every credit card and hard drive on the planet and rearrange the atoms in your body along the way. In 2004, a magnetar flare from across the galaxy briefly compressed part of Earth's upper atmosphere, a measurable planetary effect from a single stellar remnant 20,000 light years distant. But push that leftover core mass just a little higher, and even neutron degeneracy pressure isn't enough. There is nothing left in physics to stop what happens next. black hole formation, the Collapsar. Above roughly 3 solar masses of remnant core, no known force can halt the collapse. Not electron pressure, not neutron pressure, nothing. The core keeps falling in on itself forever, mathematically, without limit. What forms is a region of spacetime so warped that past a boundary called the event horizon, nothing, not light, not information, not physics as we understand it, can escape. This isn't a surface. It's a point of no return with no surface at all. Cross it in any direction, moving at any speed, and every possible future path you have left points inward. Not because something is pushing you, because space-time itself has been bent until toward the center is the only direction the future still allows. For a stellar mass black hole formed this way, the event horizon of a 10 solar mass black hole is only about 30 kilometers across, smaller than most cities, yet its gravitational influence reshapes space for light years around it. Here's the fact that changes everything. Some of the most massive dying stars don't bother forming a neutron star at all. The collapse is so total, so complete, that it goes straight from a massive iron core to a black hole in one uninterrupted plunge, sometimes without even producing a visible supernova. The star doesn't just die, it disappears. Astronomers have watched supergiant stars, hundreds of times the sun's radius, simply vanish from the sky with no explosion recorded at all, a death with no goodbye. Time itself behaves differently near the horizon. To a distant observer, an object falling in appears to slow and freeze forever, fading from view without ever technically arriving. This exact failed supernova scenario was directly observed in 2015, when astronomers watched a red supergiant 25 times the sun's mass in a galaxy called NGC 6946 quietly blink out of existence, no explosion, no remnant nebula, nothing where a massive star used to be. They call that galaxy the fireworks galaxy for how many supernovae it usually produces, and this one star broke the pattern by refusing to explode at all. The most massive collapse of all doesn't just kill a star. It erases the very rules for how the rest of the universe is allowed to watch it happen. But there's one death stranger and more violent than even this. Hypernova and gamma ray burst. This is the final entry, and it's the most destructive event known to modern astrophysics. It requires an extremely massive, rapidly rotating star, one that collapses directly into a black hole while still spinning fast enough to form a swirling accretion disk of infalling material around it. That disk channels part of the collapse into two narrow, ferociously energetic jets, blasting out from the star's poles at speeds exceeding 99.9% the speed of light. This is a gamma ray burst, and for the few seconds to few minutes it lasts, it can release more energy than the sun will produce across its entire 10 billion year lifetime. All of it funneled into a beam narrower than a flashlight, cutting through space. Here's the part that should genuinely bother you. If one of these jets pointed directly at Earth from within a few thousand light years, the gamma radiation could strip away most of the ozone layer in moments, triggering a mass extinction without a single particle of the exploding star ever physically reaching us. Some researchers connect the Ordovician extinction around 440 million years ago to exactly this kind of event. We got lucky that time, or nobody was aimed our way. Here's the twist. Because the jets are so tightly focused, we only detect a gamma ray burst when Earth happens to sit in that narrow beam, which means for every burst we see, there could be hundreds more happening, aimed elsewhere, that we will simply never know occurred. Detectors currently catch roughly one gamma ray burst a day somewhere in the observable universe, and every single one represents a star that just underwent, in seconds, the single most energetic transformation physics allows outside of the Big Bang itself. The most violent death a star can have might be the one that's mathematically invisible to us almost every single time. And that's the full ladder, from a quiet fade to a beam that could end life on a planet it never even touched. So what actually decides which of these 8 a given star gets? Line them up by mass, and the whole taxonomy snaps into focus. Under about 8 solar masses, red giant, planetary nebula, white dwarf, full stop, unless a companion star hands it a second act as a type EA detonation. Between roughly 8 and 20 solar masses, core collapse supernova leftover neutron star. Between about 20 and 40 solar masses, the collapse can go so deep it skips the neutron star stage entirely and forms a black hole directly, sometimes with a visible explosion, sometimes with none at all. And at the extreme end, a massive star spinning fast enough, feeding a disk around its own collapse, gets the hypernova and its gamma ray beam. Spin turns out to matter almost as much as mass. Two stars of identical weight, one slow, one fast, can end up on completely different branches of this tree, one quietly collapsing into a black hole, the other screaming outward as a beam that can be seen across the visible universe. Composition matters too. A metal poor star, built from the primordial hydrogen and helium of the early universe, behaves differently under collapse than a metal rich star built from the recycled wreckage of earlier stellar deaths, meaning the very first generation of stars in the universe may have died in ways no star can die today, in deaths so massive and so metal free that some theorists think a few of them may have collapsed directly into black holes weighing thousands of solar masses, seeding the supermassive black holes that now anchor entire galaxies, including our own. So here's the whole map. Low mass stars like our sun swell into red giants, breathe out planetary nebulae, and settle into white dwarfs that will still be technically cooling long after everything you know is gone. Some of those white dwarfs get a second act, stealing mass until they detonate as type Ia supernovae bright enough to measure the universe by. Massive stars fuse themselves into an iron dead end and collapse in under a second in a core collapse supernova that can outshine a galaxy. What's left becomes either a neutron star spinning fast enough to be a lighthouse, or past a certain mass, a black hole that erases itself from the observable universe entirely. And the rare, rapidly spinning giants among them go out as hypernovae, firing gamma ray beams that could sterilize a planet from thousands of light years away without so much as a warning. One mass number, one spin rate, one companion star, or the lack of one, and the entire outcome changes. Here's the part that should genuinely bother you one more time before we go. Every atom heavier than hydrogen and helium in your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing right now, came from one of these deaths. Not metaphorically, literally. Some ancient star somewhere fused it, shed it, or detonated with it. And billions of years later, gravity and chemistry arranged a fraction of that scattered material into something that could stand up, build a telescope, and ask what killed the star that made it possible. You are quite literally stellar debris that learned to ask questions about the thing that made it. Somewhere tonight, a star like the one that built you is doing one of these 8 things in perfect silence, at a distance too vast to comprehend, utterly unaware that anything is watching, or that anything ever will be again once it's gone. Not bad for stick figures on a rock,